all, I am Rajesh Pandey and I am the student of Quantology World Academy. Today we are going to discuss a very important topic from the chapter Electrostatics, Charges and Fields, that is Gauss law and its application. Gauss law. So सबसे पहले what is Gauss law? Gauss law is defined as the amount of flux present in an area is 1 by epsilon naught times the charge enclosed within it. So mathematically, if we write, we know flux phi equal to closed integration of E dot dA, and by Gauss law, it is closed integration of E dot dA equal to Q by epsilon naught. Now we will move on to its application. So its first application is electric field due to an infinitely long charged wire enclosed within an cylindrical Gaussian surface. If we take an infinitely long charged wire that is enclosed within a cylindrical Gaussian surface of length L and having linear charge density of lambda, then electric field enclosed within the cylinder will be what? And if we consider three surfaces, that is S1, S2 and S3, then the net flux enclosed will be the sum of the flux through all the surfaces. Now the flux through surface here in surface 1, the electric field and the area vector are perpendicular to each other, and in surface 3, electric field and area vector are parallel to each other. So flux through S1 and flux through S2 will be closed integration of E dot dA equal to EA cos theta. Since electric field and area vector are perpendicular to each other, therefore angle between them will be 90 degree. And we know that cos 90 degree equal to 0, so flux equal to 0. And in surface 3, flux through surface 3, it is closed integration of E dot dA, that is EA cos theta. And since electric field and area vector are parallel to each other, therefore angle between them will be 0 degree. So EA cos 0 degree, and we know cos 0 degree is 1, so it is EA. Now net flux will be the sum of all the flux through the surfaces, that is phi S1 plus phi S2 plus phi S3, that is EA. Now by Gauss law, we know that flux phi net is equal to Q upon epsilon naught. That implies EA is equal to Q upon epsilon naught. Also, we know that the area of the cylinder is 2 by RL, and also we know that linear charge density lambda is equal to Q upon L. So Q equal to lambda. Now substituting these values in this equation, we get E into 2 pi RL equal to Q by epsilon equal to lambda L by epsilon naught. So L and L will be cancelled out. So E is equal to lambda by 2 pi R epsilon naught. We can also write it as 2k lambda upon R. So this is the electric field due to an infinitely long charge wire enclosed within a cylindrical Gaussian surface. Now its second application is electric field due to a large plane sheet when a cylindrical Gaussian surface is passing into it. Suppose this is a cylindrical motion surface and a large plane sheet, large charged plane sheet is present having surface charge density of sigma. Suppose if we consider two surfaces, that is surface 1 and surface 2, then flux through surfaces 1 and surface 2 will be, here the electric field and area vector in both the surfaces are parallel to each other. Therefore, flux through surface 1 and surface 2 will be closed integration of E dot A, that is EA cos theta, and since they are parallel, their angle between them is theta, angle between them is 0 degree, so EA cos 0 degree is equal to EA. So net flux will be flux through both the surfaces, that is flux S1 plus flux through S2, that is EA plus EA, that is equal to 2EA. Now by Gauss law we know that net flux equal to charge upon epsilon naught. That implies 2EA is equal to charge upon epsilon naught. So EA is equal to charge upon epsilon naught. Here we know that surface charge density sigma is equal to Q upon K. So Q is equal to sigma A. Now EA is equal to sigma A upon it is 2 epsilon naught. So EA is equal to sigma A upon 2 epsilon naught. So here A and A dots cancel. That implies E is equal to sigma by 2 epsilon naught. So this is the electric field due to a large plane sheet passing through a cylindrical motion surface. Now its third application would be electric field due to a spherical shell having radius r. Suppose if you consider a spherical shell of radius r, then to find its electric field it would have three cases. Case 1, when field is outside the cell. When field is outside the cell, that is R is less than R. Here, this is R and this is capital R, and the inside spherical shell is charged. So by Gauss law we know that closed integration of E dot ds equal to Q upon epsilon naught. That implies E into A is equal to Q upon epsilon naught. We know that for a spherical shell, area is 4 pi r square. That implies E into 4 pi r square equal to Q by epsilon naught. That implies we can write that E is equal to Q by 4 by r square epsilon naught. Also we can write it as E equal to KQ by r square. So it is the first case, that is when field is outside the cell, that is R less than R. Then case 2, when field is at R, that is R is equal to R. Electric field is same as the case 1, that is E equal to KQ upon R square. It is same as the case 1 when R is less than R. And now case 3, Case 3, that is when field is inside the cell. When field is inside the cell, field is inside the cell, that is R greater than R. Consider a cell, and here R is greater than R. Here the outer cell is charged. Since the outer cell is charged, there is no charge enclosed within the inner cell. So as there is no charge enclosed, so Q equal to 0, and since Q equal to 0, electric field in this case will be 0. So this is the third case, that is electric field due to and spherical shape. So this is all for today, and we are enclosing this